This is Sridhar Ramakrishnan. Welcome to this month's webinar. Actually, this was last month's webinar scheduled for February 22nd, but due to an unavoidable conflict with Viktor, we've moved it to today, March 8th. Let me get started with a few bookkeeping items. The presentation will begin shortly by Viktor, and it'll go on from about 12:03 to about 1 o'clock. Professor Prasanna has kindly agreed to stay on for a few minutes after 1 o'clock in the event that there are questions, etc. He has indicated that he's got a lot of material to cover. So if there are questions by way of clarification, etc., please ask them during the as they occur to you. But if there are questions of a discussion sort, it might be useful to hold them off to the end. The slides and the recordings will be available at the end. I'm actually recording this session as we speak, and they'll be made available on YouTube, and I'll send you the link once this presentation is over. Let's see, if you've dialed in by phone, by way of clarification, you should have entered your audio PIN. That's the only way I'll be able to unmute you in the event you need to ask questions. Once the presentation begins, what I'll do is I'll unmute everyone, but please do keep your phones muted yourselves. Otherwise, background noise can be fairly distracting to both the speaker and to the other participants. And for those of you who prefer to ask questions using instant message, there's a chat window that you can see. Please enter your questions there, and hopefully I should be able to see them, or Viktor, and be able to answer, forward that on to Professor Prasanna so that you can get an answer to your question. So with that, let me go ahead and get started. Today we are delighted to have Dr. Viktor Prasanna talking to us about architectures for green routers. It's a fascinating topic about which I'm sure with all the emphasis on green technologies, green data centers, there's some interesting material here that we all want to hear about. Professor Prasanna is at the Department of Electrical Engineering and Computer Science at the University of Southern California. His research interests include parallel and distributed computing, including network sensor systems, embedded systems, configurable architectures, and high-performance computing. He is currently editor-in-chief of the Journal of Parallel and Distributed Computing, also the founding chair of the IEEE Computer Society Technical Committee for Parallel Processing, and he's a fellow of the ACM, the IEEE, and the American Association for the Advancement of Science. Needless to say, I'm very delighted to have Viktor join us today. And on a personal note, Viktor's group has been doing some great research in the area for high-performance computing algorithms. We've had actually a couple of students of Viktor's who have actually presented in the past. So with that, I'm going to turn it over to Professor Prasanna.
Thank you, Sridhar. I'm getting this started. I just want to make sure we're all set. We're okay to proceed, Sridhar?
Yes, we are. Thank you.
Okay, good. Assume that all of you can see the screen. The screen now you should be able to see architectures for green routers. That is slide number 1 I have. I had put together the next slide here, which was actually the information that was already given to you by Sridhar, so I'm going to skip through this slide number 1. So I am on slide number 2. Let me stop here briefly to kind of give you some overall context, just to kind of get a perspective on what I'm trying to do in this particular presentation. So what I did was that I went through some of my slide collections I had, just looking at some of my recent students, Birong Jiang, Edward Yang, and Hong Lei. They all have graduated over the last few years, and they're all doing wonderful things in their lives. I just borrowed a number of slides from their presentations, put together a few more slides on top of that. So I think you'll see a kind of a collection of topics that I'm covering here, all in the context of designing high-performance routers, which have a high throughput as well as a low power consumption. So before I go into this presentation, I also would like to welcome you to visit my website, where I've listed the various projects we are working on. We are also doing work in other aspects of high-performance computing, parallel computing. We are looking at multi-core systems. We have several new data. One of the projects is looking at using the next generation of embedded processors and see how do we get high performance as well as low power dissipation for various signal processing, image processing, benchmarks that the government community is interested in. We also have working on some of the big data projects. We're looking at graph time series graphs, and then looking at what are the techniques to parallelize those kinds of applications on cloud platforms and other tightly coupled systems for graph applications. We also have a large project from the Department of Energy on smart grid, in which we are primarily focused on demand response optimization, where we are looking at some real-time data coming from smart meters, and then doing some data analytics on top of that to be able to understand how do we reduce the peak demand on a particular utility system, and that is being deployed on campus here at USC, and ultimately as the project concludes, some of the ideas from that will be used in the Los Angeles area by the Los Angeles Department of Water and Power. So with that kind of the big picture, all these projects are all listed from my website. You can access them. So today I will talk about green routers. By green routers, I'm referring to obviously here power is an important metric here. What is the amount of energy we spend as the packet goes through the internet backbone? That's what we're interested here. So we would like to make sure that these architectures we develop have high throughput. Today we're talking about hundreds of gigabits per second throughput, and at the same time they consume, they have a small energy footprint and actual implementations at very high data rates. So I've organized this talk to give a high level, to look at the reconfigurable computing systems, FPGAs, just to give you some background. Some of you may already know about it. I will also talk from a historical perspective here. Now, we did a lot of work in the 80s and 90s. We're looking at a theoretical model of computation for FPGAs and reconfigurable computing. There's a whole lot of theoretical research in this area. I'll just briefly touch on this to give you a sense of what is it we could do if runtime or dynamic reconfiguration is available, and some of these devices support some of these features, so we can get high performance by exploiting this dynamic reconfiguration. Then I'll jump into green routers, which is the heart of this presentation. I have a number of applications I'll talk about, starting from packet classification, going on to IP lookup problem, and then going on to what is called deep packet inspection, where we are doing regular expression matching or pattern matching kind of applications, where we have large number of patterns, and we would like to be able to look at those patterns, and then on a very high traffic rate, say hundreds of gigabits per second line traffic rate, we want to be able to see how do we match these patterns and understand if there is any malicious traffic going to the internet backbone. I'll have some concluding remarks. I should also encourage you to ask me any clarification questions as we go along, and then discussions we can have towards the end. I've set aside about 5 minutes. Again, I won't be able to cover all the slides in detail. I'm going to leave the presentation with Sridhar, so you can look at them, and then if you do have any questions about this talk as well as the other projects I mentioned, I'll be very happy to correspond with you offline via email, or also encourage you to contact me if that makes sense to you. So I'm going to giving a big picture. The work we are doing here is in the broad context of building the cybersecurity architectures, which I've shown you an example of that, where we are using multi-core, many-core kind of processors, GPUs, for doing some kind of machine learning to understand traffic patterns, and then later on to actually do the line rate classification problems using devices such as FPGAs to be able to get high performance to satisfy very high throughput in those implementations. So, so in this context, we are planning on using all these kinds of processing capabilities, multi-core, many-core processors, GPUs, as well as FPGAs in that context. So today what I'm going to be doing is focus primarily on the FPGA portion of this scenario here, where we're interested in, we have already learned the patterns, we already know the routing tables to be used, and then how do you perform these operations at very high line rates, and at the same time ensure that the power dissipation is within certain bounds available in those routers. So this slide, the next slide is talking about what are the requirements you have and what are the challenges. The main challenges you face here are that the throughput rates are extremely high in these applications, hundreds of gigabits per second, which translates to hundreds of millions of packet lookups per second that you need to be able to perform in these architectures. The filtering rules can be large. IP prefixes could be We are now talking about hundreds of thousands or even a million IP lookup prefixes in the backbone routers. The number of rules you have in the context of this classification problems, or if you're looking at open flow kind of a architecture now, large number of fields as well as a number of rule sets, number of rules in the rule set can also be very large. So we're going to be able to deal with these kinds of large rule data sets that comes into picture while we implement these on FPGAs or multi-core or GPU kind of GPU-based systems. So what it means is that sometimes we will not be able to store these patterns completely on the FPGA device. We may be exceeding the available block RAM or the available static memory available in this system. So we will be forced to use external memory, which will add a large penalty for the performance due to the access latencies you have in those systems. So this work is exploiting. In fact, we've been doing this work in the reconfigurable computing area since late 80s, early 90s time frame. The key idea here is that we want to be able to look at systems which can be configured, meaning that we could vary the connection patterns or the local memory storage, the data stored in the systems, so that I can get the benefits of both something like a microprocessor, which is completely flexible to use, or that of a application-specific system, which is going to give you the highest performance but the lowest flexibility in terms of being able to map various applications onto the ASIC device here. So reconfigurable computing, the promise here is that we will be able to get high flexibility as well as high performance, because at runtime we are able to reconfigure the device to be able to suit the requirements of the particular application we have. So, so in this context, reconfiguration here means that going from a particular configuration in which you have a particular functional unit set up on the device to be able to configure that to be able to solve an alternate problem by changing the configurations. For example, the logic may be you configure to perform an arithmetic operation like multiply. After a few cycles, you might want to configure that to perform an add operation. This is what we mean by reconfiguration. That means at runtime, we realize various functionality by being able to configure the basic units of the operational units of these FPGA devices or reconfigurable devices. There are many ways of doing reconfiguration. One is called static reconfiguration. That means you get all the configuration you want on the device statically at the design time before the operation starts, and then you don't change the configurations at all. A lot of the FPGA applications are in this space where you configure the device once and repeatedly make use of it without having to change those configurations as the computation proceeds. What is interesting, both from an algorithmic as well as from a theoretical perspective, is that dynamic or runtime reconfiguration, meaning that as the computation is proceeding based on the input data, based on the decisions you made so far, you want to be able to change the functionality, which is something that can give dramatically improved performance if you're able to perform these kinds of reconfigurations very quickly on the fly at runtime. So before I go into the specific architectures we have developed to be able to get this high performance and low power dissipation for the internet routing or from packet classification kind of applications, let me just give you a very, very brief overview of what these FPGAs mean. These are the devices in the market produced by various companies like Xilinx, Altera. From a very high level perspective, these devices consist of logic cells, what I see here in these small boxes, and some connecting patterns between them. So I can synthesize a particular application requirement functionality by configuring those logic blocks, by actually writing into those memory locations of those logic blocks we have, and then also figuring out and then implementing those connections between those logic blocks. So I can build, for example, an adder at this point on the upper right-hand corner here by using various cells depending on the number of bits I have in the adder units to be added. So I can build those particular adder or a multiplier by configuring those individual logic cells and making the connections between them. That is the basic idea of using these FPGAs, and configuring these devices means that I'm going to be writing something into the local memory of the what are called LUTs or lookup tables you have in those implementations. The technology is advanced quite a bit over the years. In the last 15 years, if you see here, the state-of-the-art devices in the market today are extremely capable devices. Very high data rates can be sustained by them. These technologies are very similar to the technologies used in the state-of-the-art multi-core processors in terms of fabrication technology. and they can give extremely high performance in terms of number of logic operations, the number of basic operations you can do per unit of time, in terms of the input-output, in terms of the amount of storage you have on these devices. So we can get extremely high performance computation communication by using these devices in many of the real-life applications. Just to give you a sense of what we can do in the market today, I've just listed here what happens in a typical device in the market. A device like this has, in addition to the basic logic cells and the interconnections between them, there's a large amount of what is called BRAMs, which is approximately 46 megabits is available in a typical large device in the market today. A very large number of basic building blocks called your slices. And then there is also what is called a fixed point arithmetic slices, approximately 2,000 these are available here. You could use them to perform various DSP operations. And there's also a lot of other details I'm showing here, which is in terms of the input-output here, the interconnections you can do on that, and also some of the hardware details in terms of how the clock is going to be distributed across the complete system we have. So let me switch gears. I would like to go towards, take you back to late 80s, early 90s, where these kinds of devices were not really available those days. And then how the technology and what kind of computational abstractions people were talking about. In fact, we proposed some of the very early models in this area, what we call the reconfigurable mesh model, which was an abstraction of the kind of devices to come, and then see what we asked the question, if those devices were going to be available, what is it we could do from algorithm design, from a theoretical perspective. And the basic idea that we had was that the idea of having a two-dimensional mesh was very popular those days. And we asked the question, if we take each processing element we have, and then for each one of them inside the processing element, suppose we place all these switches. I'm showing here that all of those 6 connections we have. For every connection inside the processing element, there are 6 connections that we place an extra switch on them. That means each one of these boxes you see here, this can be on or off. And we can make various connecting patterns by connecting these boxes on or off. And we assume that, let's say that in every clock cycle I have a control over this. So for example, I can make a horizontal line here by closing all those switches along that line here. Or I could make vertical buses by going along the vertical lines I have here and closing all those vertical switches we have along those the 4 columns we have. Therefore, I can build 4 vertical lines of size 4 by looking at those 4 columns of P's we have. So all these connecting patterns can be realized very quickly, very efficiently in the reconfigurable mesh model. So what it means is that if I give you these inputs here, I could, for example, build a binary tree on this here very quickly by making those connections and building the connecting patterns by closing or opening those switches you have inside the processing elements. This particular work appeared quite early in the MIT Research Advanced Research in VLSI conference in 1989. And a lot of other papers have appeared how to use this model, what is the power of reconfiguration if you have such connecting patterns available to us. I'm just showing an example here. If you had a one-dimensional reconfigurable mesh and you want to add, say, 2 numbers, I'm showing here 2 5-bit numbers to add here. The idea is very simple. We look at these numbers and then say, what is the basic full adder functionality we have? If one of the inputs is equal to 1, whatever carry input is coming should be propagated. So we close that switch. If both the inputs are 1 here, I'm going to be generating a carry at this stage. That's what I'm doing here. I open the switch here and push a 1 signal to go this way here. So this 1 signal propagates, this 1-0 combination here. So it propagates all the way. Therefore, all these processing elements can locally compute their output, which is the exclusive OR of the 2 input bits we have, and the carry input, the full adder functionality we can implement using a lookup table there, for example. Therefore, I can compute the addition of 2 numbers very, very efficiently. So in the constant delay model using this particular reconfigurable mesh model, you could add 2 numbers in constant time. So I can add 64-bit numbers by just basically configuring this based on the input data we have and propagating those signals through the entire device to be able to solve these problems very, very quickly. So I'm just showing another example here.
Victor, I think there was a question that was sent to me by chat. The question was, how do you prevent loops? Somnath, if you're here, if you have you can actually ask the question directly as well. I apologize, my voice is a little bad today.
That's okay. That's a good question. So the question was that how do you avoid loops in a situation like this? So by definition of the algorithm running on this machine, that you are required by algorithm design to ensure that a particular set of connections, particular set of rules are followed here. Rule number one here is that if you make a wiring connection, for example, I'm showing in this diagram a connecting wire that is going all the way from here like this. This is the connection that is established here. The rule number one is that whatever algorithm you design, whatever algorithm that specifies these connections to be made, should ensure that exactly only one of the connecting processing elements can put a value on that. That is the rules of engagement here. That means that if I have these connections here, I cannot have this processing element as well as this processing element trying to send some signal on this. There will be conflicts on this bus. The other rules include to address the concern that has been expressed here, what happens if there are loops. We will ensure that there are no loops in this connection. If there are loops here, signal will propagate through all of them. If we do have the loops, we can also make sure the loops are okay by ensuring that exactly one particular signal will be put on this bus. So I think the short answer to the question here is that we have to design the algorithm so that the physical properties of the device on which it is going to be implemented are satisfied. We cannot have multiple processing elements talking at the same time on the bus.
Okay, thank you.
So I'm going to the slide here of the exclusive OR computation. Just to illustrate how powerful this device is, this particular reconfiguration capability is that what this is showing you is that it is possible to compute the exclusive OR function, which is a difficult function to compute in terms of the amount of logic resources you need if you want to compute this function very, very quickly. What this is showing is that if you have n bits and you want to compute the parity of this n bits, you can take a reconfigurable mesh here having 3 rows and 2n columns. N is the total number of input bits we have, and by establishing these patterns locally, we can compute the exclusive OR in constant time by using a linear amount of resources, linear in the number of input bits we have here. The idea is very simple. Whenever the input bit here, if you look at these first 2 columns here, if the input is 1, whatever is coming in these 2 lines are switched. What is coming in this line is going up. There are 2 input lines I'm showing here, this line and this line. So those 2 lines are switched. That's what the connecting pattern is happening here. And if the input is 0 in this case, this B of 1 is 0 here in this input, then input is all straight connections. So you can kind of see you can see the intuition behind it here. Every time I find a 1, I'm going to be changing the value of the output, and that's what is the switch operation I'm doing here by connecting patterns. If the input is a 0 at that point, whatever I've computed so far is a final output. So I'm just going to keep pushing it forward from that particular stage. So I won't go into much details. In fact, there are workshops, conferences that talk about these kinds of architectures in detail as alternate models of computation and what is the power of such kind of models in solving complex problems. So I'm just showing here that there is a whole lot of research. For example, you can compute the product of 2 integers very, very quickly by using an n by n reconfigurable mesh. You can multiply 2 n-bit numbers in constant time. You can compute the fast Fourier transform very efficiently. You can do sorting very efficiently. You can also implement division circuits to solve the division problem in constant time by using dynamic reconfiguration. Most of these results, you will get them either through my website or going through various conferences in the last 15-20 years. These results have been published about understanding the power of dynamic reconfiguration. So let us move on. So I would like to now focus on the main topic here. So we want to be building these high throughput routers where we want to ensure that throughput as well as power dissipation, power performance are addressed, keeping in mind that the routing table sizes are growing. The routing tables are becoming larger, the number of patterns you're matching for DPI is increasing. Is it possible to solve these problems while simultaneously sustaining high throughput and low power dissipation measured, for example, in terms of what is the amount of power consumed per unit packet routing through your network, taking a particular fixed amount of packets, a fixed amount of table size for the rule sets you have in those implementations. That's kind of the big picture of where we are headed in this work. To reiterate what I said, these routers do a lot of work. For example, they do IP lookup, they do flow detection. For example, we can do particular kind of traffic classification using machine learning techniques. You can do multi-field classification. For example, 5-field classification is very common. So there is a number of operations these routers are doing. So we look at individual these operations and then see for each one of those operations what are the architectures we can build and how do we get high performance from those implementations. So just giving some background on the problems we are solving. In the case of the router classification problems, so we have various rules. This is given to us. This is sometimes the rule sets are changing dynamically at runtime. So essentially, you look at the packet header and then route to one of those output ports based on the rule sets we have here and what are the matches you find between the header and the particular rule set we have. That is going to be the simple problem of classification and then routing. So the packet classification problem, the previous one I talked about, just look at the header, look at the destination address, and then do routing. The classification does some little bit more sophisticated. It does look at the more number of fields. In this case, I'm showing here source address, destination address, source port, destination port, and the protocol. Based on all these 5 fields, you decide where to route this payload as it goes through the router. Now it is possible that the number of columns, number of fields I'm using here is even larger. For example, if you're looking at the open flow standard, we have a lot more number of fields here, 12 fields. Is currently extended up to 40 fields we have here. So the various rules are specified here, and then these rules specify what is the value here, what kind of matching you're doing. Sometimes you may come and tell me, look, in that particular field, ignore whatever is there and do the routing for me, or what's called a wildcard. There are a number of ways of specifying what to do in those individual fields, and then you combine the results of these individual fields, for example, and then decide where a particular packet is going to be routed through your router. So the IP lookup problem is something we are going to study in detail here in this presentation. We have studied this with a PhD thesis. In fact, a couple of PhD students worked with me on this particular problem. So the routing table is a collection of prefixes given to us. The problem here is what is called longest prefix match, that we want to be able to look at the incoming packet header, look at its destination port address. And
can I interrupt for a second? Can you please make sure, everyone, that you keep your phones muted unless you need to ask a question. Otherwise, we're getting some background interference. Thank you. Go ahead, Victor. Sorry. Okay, fine. So our problem here is that multiple matches can occur when an input packet header comes, and we want to match it to the output forwarding port here based on the longest prefix match. I'm just giving an example here. If the input IP address is this, it is going to match both of them up to this point. It also, this is the longest matching here is with respect to the second table entry I have here. That means it is going to be routed to port number 1 in the longest prefix match for the IP lookup problem. So there are a number of challenges. In fact, there are a number of companies that are organizing conferences, workshops in this context. There is a very well-known Cisco Green Symposium that looks at these kinds of problems. And then there's quite a lot of data available in terms of what kind of throughputs are expected and where the power dissipation occurs in these kinds of routers, as well as what is the expectation in terms of going forward, in terms of how much power do you dissipate per packet going through the routing backbone. So I'm showing this interesting diagram here, which is one of the reports produced from Bell Labs, that is looking at what is the impact of the backbone, the internet backbone, on the overall power dissipation in the context of information and communication technology, ICT infrastructure here. It's interesting, the horizontal axis here is the time axis. This date here is 2009 here. And it is showing that as time progressing here, you'll find that more and more energy is spent in this backbone routers, internet routers here, compared to what is happening in the context of servers and the basic data processing they are doing. So there's quite a lot of energy being dissipated in the backbone, and it makes sense for us to be able to reduce the power dissipation in those routers. This particular chart, again borrowed from Bell Labs, is showing here how the power dissipation per for the power density in these routers.
the important point, the take-home message here is that as we are going here in the horizontal axis, going forward here, there is going to be a shortfall here measured in terms of as the throughput is increasing here also in the vertical axis. What can be supported on a single line card here, the power dissipation on that cannot support the kind of throughputs that is expected as the throughputs are increasing, the router capacities are increasing in these routers in the market today. So if you look inside the router, what is happening, what this diagram is showing is that approximately 2/3 of the power associated within a router here is going to be in the layer 3 function. Layer 3 function corresponds to this problem such as IP lookup and packet classification, and we are interested in seeing what architectures we can develop to attack the power dissipation in those basic kernel operations, the IP lookup problem as well as the classification problem. I will also talk a little bit about the deep packet inspection, which is also one of the router functions where you want to, for example, build a more secure systems, that we would like to be able to go inside the packet payload also, and then understand what kind of traffic is flowing through your system. So our research here, from our academic perspective here, we are interested in modeling these devices at the level of building this FPGA-based systems. We are going to be concerned about making these devices to be flexible, making these devices to be scalable in terms of the routing table size, in terms of the number of rules we have in the classification problems. And we also want to make sure that we also preserve the order in which the packets are coming into your system. So kind of a first in, first out kind of a policy in terms of the way the routing decisions are made and how the packets exit the router we have. Obviously, we are concerned about low power dissipation. All our implementations, we are measuring power by using established tools available in the market, and then understand the throughput versus the power dissipation performance of these routers. So this problem is a classic problem, the problem of building these routers. In fact, a classic solution to the problem is very, very simple. Essentially, what we can do is that we can take all the routing rules we have here and put them in a large content addressable memory called TCAMs, and then just do in a single clock cycle. You can go and search in parallel, and then you can decide where the destination address is going to be, which is a classic solution to the problem. As I'm showing here in this table, these TCAMs consume a lot of power. Also, the clock rates of TCAMs, of course, these numbers change. I'm just showing an example implementation, say 2 years ago here, and so there is a wide variation in performance as well as in terms of the amount of power you're going to be dissipating in those devices, and that gives us opportunities for us to think of using traditional SRAMs, DRAMs. There are variations of DRAMs specifically designed for router applications. Can we use these kinds of lower power devices, which are also high density devices? You can get very high density in those devices in terms of the number of bits you can store in that device. Can we exploit those kinds of devices and then get high throughput and low power in the process of implementing them? So I'm going to be looking at all these 3 problems, and I promise you that I won't be able to cover all 3 of them in detail. There are a large number of slides essentially targeting some of the recent work we have done in this space, looking at classification problems. We have some new results. We also have looked at the IP lookup problem, and we also looked at the deep packet inspection, the DPI problems, where it's a classic problem of being able to match regular expressions against incoming high throughput rate traffic for the internet backbone. So we are looking for pipelined architectures because a lot of our implementers essentially are doing something like this. There is some kind of a tree structure, trie or a tree is going to be used, and then we partition that and then map it onto the target architecture, and then we do the comparisons level by level, meaning that by pipelining it, we can get very high throughput by being able to, for every clock cycle, which is corresponding to the amount of operation you do in a particular level of this tree here, we can push these packets at a very high rate through the system. That gives you very high rates and clock rates, very high throughput from the implementation point of view here. And then I will talk about some of the partitioning problems that comes into picture. So one classic problem here is that if you want to reduce the power dissipation in these routers, what are the techniques that we can do here? So one way we can do it here is that if I'm doing IPv6, don't do 64 levels. Other alternate ways by which we could group those levels. For example, you can talk about multi-bit tries that comes into picture. We can reduce the amount of accesses, number of accesses you do, and then you can also reduce the selectively turn off some of these VRAMs or the storage devices you are using in the particular router, simply because the packet that is coming there will not traverse a particular path in the tree. Those are the kind of techniques that we use here to be able to reduce the power dissipation in these mappings here. I'm just showing a very high-level conceptual view here. So this particular routing table is represented in some graph structure, a tree structure, or a trie structure, and then that is partitioned and mapped into various pipelines. And then as the incoming packet comes, it goes through one of these pipelines. That means you can turn off the other pipelines, and every clock cycle you can receive an input, and that gives you very high throughput to process those incoming packets. Of course, there is a small overhead here. This is the index table, which is responsible for figuring out when the packet comes here, which one of those paths it should take here. This index table can become complicated depending on the way that you partition the input and then partition the input trie here you have for that particular routing table, and then map them into the various pipelines you have in the implementation. So to summarize this line of thinking, each packet goes through exactly one pipeline. Therefore, I can deactivate the other pipelines. And also, while you are going, the pipeline is going to be deactivated. If it is not, the packet is not going to be traversing because only one of those pipelines is going to be traversed. We bound the height of the tree. That reduces the number of memory accesses you do. Because you partition the tree, that means I don't have to activate the entire memory that is used for storing this tree. That also reduces the power dissipation you have here. And finally, we also ensure that across the various pipeline stages you have in every pipeline, we make sure that the memory distribution is uniform. This ensures that the peak power dissipation is also going to be controlled, so that we don't have variation as we traverse various stages or the various pipelines you have in these implementations. So I'm going to skip some details here about how to build the tree here. The essential idea here being that we want to reduce the height here by using the grouping multiple number of nodes, multiple number of layers, multiple number of levels into a single level. And then we also need to do some load balancing across the pipeline stages. We have developed a number of heuristics for doing it, and then based on that I'll show you some experimental results here for the various routing tables that we have considered here. So we've taken various rule sets. What is shown here is the various available rule sets in the research community. And then I'm showing here in the diagrams, trying to measure here as you increase the number of pipelines, can we still get a uniform distribution of memory across those pipeline stages? And that is showing here for the various number of pipelines here at 2, 4, 6, and 8. It is also showing here what is the number of pipeline, amount of pipeline depth here, and how is the distribution across those pipeline stages you have, that we get uniform distribution for the 5 different example of rule sets we have taken here. And that is what we are showing here, that for all of them here we get very nice uniform distribution here across the pipeline stages as you vary the number of pipelines. So let me summarize here. We have done detailed experiments. These are published in the literature, and then we have also compared this against other pipeline, other partitioned implementations. And these comparisons were performed by using state-of-the-art device tools for understanding the memory power dissipation here. I'm comparing against something in the market here called CoolCam, which is a TCAM-based solution in which partitioning is employed here. And then based on our experimental results, so we can get up to 40x power performance improvement and also approximately 12x improvement in throughput by using multiple of these pipelines to be able to implement the complete lookup problem we have. So let us move on. So the previous one, just to summarize where we are at, we looked at this classic problem here in terms of this classification problem here, and then we said that it is possible to do this kind of a tri-partitioning and mapping here to ensure that we can focus towards having a partition structure and then selectively deactivate the pipelines to get very high performance in terms of power improvements in these implementations. So what I'm doing next is to look at the IP lookup problem. The IP lookup problem, as I said earlier, is the longest prefix matching problem. in which a large table is given to you, typically in the range of few hundred thousands or even millions of entries. And then each entry is a prefix of the example I've shown here. It could be 32 bits, it could be 64 bits, depending on IPv4 or IPv6. And then for each entry, it tells us here, if the longest prefix match occurs here, this is the output port to be used for forwarding. And then given an input prefix that comes to you, a destination port address, you match it here in this column. And then among all possible matches you find here, the prefix matches you take the one that has got the longest match here. In this case, if the routing table consisted of 2 entries here, this is going to be the longest prefix match here. Therefore, the incoming packet is going to be routed to port number 1. So the simple idea that we used here is that how about we look at this as the non-overlapping ranges in those prefixes we have here, and I'll talk about how to get those non-overlapping ranges in a minute, and then organize this as a binary search tree. In fact, organize this as a complete binary search tree. The advantage here being that in the complete binary search tree case, I don't have to explicitly store all the pointers from a particular node to its children. That saves a lot of memory for us, as well as a lot of power dissipation is saved in this. In fact, in these applications, most of the power is dissipated in the memory storage. So by using this kind of a complete binary search tree structure here, we can significantly reduce the amount of power that is dissipated here. And we can also use external SRAMs if more storage is needed here. So I'm going to skip many of these details. The key idea here being that incoming packet, it goes to a unique particular match that is here. This match corresponds to a particular prefix I have here. So you organize all your prefixes into a disjoint, non-overlapping ranges you have here, and then build a complete binary search tree out of it. And then incoming packet, you compare and follow this particular route here, and then go to the destination that's going to be a leaf node you have in this implementation. I'm showing here the experimental results. We considered various IP lookup routing tables available in the literature. I'm showing here the distribution of the prefixes. Typically in this, I'm looking for IPv4 here, and large number of prefixes are in this range here. Somewhere between 22, 23, 24 is where most of these prefixes and typical routing tables are going to be. So there's quite a lot of algorithmic optimization that goes on behind the scenes here. I'm not covering those details. All our papers, if you look at related papers, you can find these optimizations. Essentially, what we are saying here is that we look at this range of distribution of prefixes. We do partition this range. That gives us different pipelines to be used. And then within each one of them, we'll make sure that we build a range tree for the particular prefixes we have, and we want to make sure that the prefix overlap problem is solved. We can solve the prefix overlap problem by looking at where the transition points are there in the range tree, and then make sure that for every input you got an exactly one leaf node, which gives you the output routing table information for you to use that. The overall architecture looks like this. The various pipelines corresponding to the prefix partition that you obtained, and we can also have a buffer for new prefixes to be added. And also for small size prefixes, maybe it just makes sense for us to do a direct memory access, maybe up to say 12 bits or 14 bits of prefix. We do a direct memory access, random access, and then figure out the routing to the output. So power optimization, the important idea to notice here is that because I've partitioned it, the complete space of the prefixes I have, I'm going to be activating only one of those one of those particular paths is going to be followed in the routing. Therefore, what it means is that if the n is the total number of nodes I have in the particular range tree I'm implementing here, I'm going to be only traversing a particular path. Therefore, the power optimizations by selectively turning off the non-traversed path trees you have, storage you have in this implementation, I can get a power performance improvement of a factor of n over log n, which is going to be significant. And this particular other constant shown here is a constant that is absorbing the basic size of the block RAM that is used in those implementations. There's also other optimizations we can do. For example, we can do cross-pipeline optimization. The idea here being that if you are finding a longer prefix match, then I don't have to do the shorter prefix matches in the other pipelines. We can share the information across the pipelines, and then you can also obtain more performance in terms of power optimizations by further optimizing which pipelines to which ones not to run once a particular stage in the search tree has been reached. So we have done these implementations. This is an implementation done a few years ago on the Vertex 4 device. And then I'm showing here what is the power performance here in terms of the clock rates we have obtained here, how much power consumption was observed here for the particular Vertex 4 implementation we had. To summarize this portion of the work, I'm comparing here the power consumption against the TCAM-based implementations. Normalized here refers to if we were to use the same size routing table on TCAM, what would happen. And this particular experimental result is showing that up to 4x performance improvement can be obtained in terms of the dynamic power dissipation in these devices, as opposed to using a large TCAM for storing the entire routing table for the same amount of throughput and for the same amount of the number of prefixes or the routing table size you have in our implementation. So let me move on to the next problem, which is the problem dealing with deep packet inspection. At a very high level, what this problem is doing is that it looks at the payload also. So a simple definition of this problem is that we have been given large number of patterns. We can represent those patterns, for example, as regular expressions, which is a more compact as well as a more richer way of representing what this matching should be. And then a large number of such expressions are given to us, and we want to be able to look at the entire payload and then see if there are any matches occurring, and then take corresponding actions based on the particular match that occurs in the incoming traffic. So now when we do this, throughput is important. The number of regular expressions used in those implementations is important, and we also want to ensure that we can implement them by exploiting some of the features of the FPGA devices, so that very high performance can be obtained by exploiting the individual connections you have on those FPGA devices. This portion of the work here gets into how do you take the particular operations you do in the regular expressions and how do you map them into hardware. I won't go into a lot of details here. I'll just give you some very high-level view. I'll go to a particular construction method that we proposed. This particular construction method, the upper portion you see here is what is called McNaughton-Yamada construction. This construction has been known since late 50s, early 60s here. Essentially, it gives you a method by which, given a regular expression, how do you convert that into a non-deterministic finite automaton? These are all the steps shown here for the various ways of combining regular expressions, combining individual patterns, and building a longer regular expression by doing these basic operations of concatenation, clean closure, looking at union of regular expressions, and that is what is shown here as this construction here. The key idea of our construction is that in this method, if you look at it here, there can be long wires in your hardware implementation because of this what are called epsilon transitions. You see this epsilon coming here. Essentially, I connected this particular regular expression with this one here by making this connection as a zero cost transfer. Therefore, I can advance from this state here to this state without consuming an input character. So if you have such connections, for example, here I can have something that is, if I connect this portion and this portion here, this can be something that goes from here. It could have epsilon transitions there also, go one more here, and then go like that. It is possible to have a long chain of epsilon transitions. The problem with this is that if you implement this on FPGAs, if you build a circuit for that, that can result in long connecting wires, meaning that your clock throughput is going to be low in those implementations. So we came up with an alternate construction here. We call this the modified construction here, the lower portion you see here. The key idea here is that when you combine these regular expressions, why not allow multiple transitions? Therefore, I can increase the out degree of a particular node at the expense of increasing the out degree of the nodes we have when we connect these individual expressions. I would like to make sure that the long wires are only wires of length equal to 1 in the connecting edges we have. Well, length equal to 1 meaning that I don't have go from A to B, B to C, C to D kind of connections coming into picture here. That means that every time I do an epsilon transition, I'm guaranteed that I have a non-epsilon or a character transition that is going to be affected. And that is what I have summarized here as a particular claim here, that there is always going to be in the modified construction method, it is going to be alternating paths between epsilon and non-epsilon transitions, or label transitions we call them, that ensures that our clock rates are going to be high in those implementations. So I'm going to be, as promised, skipping a lot of details here about how to do this particular implementation. I would like to keep some time for discussions towards the end. I'm just showing an example here. This is the classic way of building a non-deterministic automaton given a regular expression. This is the example expression I have here. This is our alternate way of building it here. All these dotted lines you see here are all the epsilon transitions. And in this particular example, you can have a transition that is of length 2 here, or even longer transitions you can find here. For example, I could have gone from this state through this state here, all the way like this to one of the states like that. Up to 4 epsilon transitions is possible. This is our architecture, our NFA architecture, by using our modified construction, with the nice property that every time I do this epsilon transition here, for example, I did this transition here, the next transition out is going to be a non-epsilon transition here. That is true for any path you take here. Every time I do epsilon, there will be non-epsilon. That ensures that input character is consumed, and that also ensures that we don't have long wires in the resulting implementation. So let me give just the gist of the idea of implementing this, and I'm going to skip all the details after this. The main idea here is in this diagram. What we do is that these are all these states I am showing here in blue, and we'll map those states into the individual flip-flops I have in the FPGA implementation. And all these connections logic you are seeing essentially is capturing whatever connections you have here. Just a simple example, if you look at state number 3, incoming edge here is C. Therefore, if you look at state number 3 here, it's the input character. I decode that by using this, and that is AND signal here. Then I go to this state here. If any of these conditions are satisfied, input arrows coming from state 3 or state 2 or state 1, and that is what this OR gate is doing here. That is the simple gist of what the construction is. So there's a very natural way to construct this NFA and then map the NFA into the FPGA hardware we have using the logic resources and the routing resources. That gives a very nice implementation of the regular expression on the FPGA hardware. There are a number of other tricks we can do. For example, we can combine these NFAs to give you to be able to read more than 1 character per clock cycle. That improves the throughput by being able to consume more than 1 character per clock cycle. So I'm going to skip all the implementation details here. I'll just go through some results here. I'm showing here the kind of throughput you can get here, and also showing here as you vary the number of input characters per clock cycle, you vary the number of input characters by stacking the hardware, and that can give you higher performance here. We have made these implementations using various Xilinx devices. And all these numbers you see essentially are the various number of expression matching engines patterns that we collected, and we implemented them to show what kind of performance you can get in those implementations. So let me conclude. Our interest is driven by looking at these kinds of fine-grained devices and then exploiting various architectures on top of them. By architecture, I'm referring to we are building some kind of a virtual architecture on top of the FPGA architecture, and that virtual architecture maps nicely into the physical hardware, and that gives you high performance. And then we do a number of optimizations by using the memory effectively. The memory here referring to the distributed RAM or the block RAM in these devices. And most of the power that is dissipated in these devices is in storing and accessing these routing tables as tries or tree structures, and then control that power, and that gives you higher performance in these implementations. We have a number of ongoing projects. For example, we're looking at the software-defined networking space where open flow is used, and then we have some implementations now that is looking at how to improve performance by looking at large number of fields you have in this IP in this open flow format, and then be able to map them onto hardware as well as the software. The software I'm referring to the multi-core or many-core implementations. So I think I should stop here, Sridhar, and then take some questions if there are any.
Yes, thank you, Professor Prasanna. Let me do the following. Folks, for those that need to ask questions, make sure that you unmute yourself and ask the question. If you prefer to send the question to me by chat, feel free to do that, and I'll relay them on to Professor Prasanna. I guess while you guys are getting started, there was one question that already came in a little while ago, Professor Prasanna, and it has to do with, turning off and turning on the pipeline. The question had to do with who does that, and what's the process that governs, the turning off and on of the pipeline?
Right. Okay, so it's a very good question. So just to repeat that, in one of the earlier implementations, we claimed that we can do power optimization by selectively enabling the various pipelines. That is possible algorithmically because every input packet will go through exactly one pipeline because of the way the tree or the trie structure was partitioned. So the question is that who does that and how it is implemented? Who does that? We have the initial, in front of those pipelines, we have a small hardware that is the index table hardware, which could be a small CAM, where essentially makes a table lookup and decides which one of those pipelines to be used. So the decision making is going to be done in that initial stage, which tells which way the packet header is to be routed. Now the actual hardware for implementing it, the technology we are using is what is called clock gating. Which is available in this FPGA devices. For example, we're using Xilinx devices where we can dynamically activate or deactivate a particular logic path, and that's what we're doing here. So that gives us a control over how to deactivate a particular pipeline. Okay?
So I have a question.
Yes?
I'm trying to understand the role of the FPGA. If you were to take, for example, the trie pipelines that you showed, can you build on an ASIC a programmable pipeline processor that implements the tries as you see them, or does the whole process fundamentally depend on the FPGA? So is the FPGA a convenient way to implement what you have that you don't have to go to fab, or is it fundamentally the best way to go?
So actually there are two questions. I think the first portion of the talk in which I am looking at them as data structures and mapping them into hardware. The mapping actually is a linear pipeline architecture. So I'm not really exploiting in a particular feature of FPGA. It is not something only FPGAs are good for implementing. In other words, I could have taken those architectures, built some SRAM, built a processing engine, the pipeline stages I could have done them on ASICs also. So for the IP lookup problem and the classification problem that I showed here. Now the question becomes slightly different if you look at the DPI problem I showed. In case of DPI, for every regular expression that you give me, I actually build those connecting patterns. Okay, so I think I can't go back in my slides here. So given the expression, whatever those AND gates, OR gates, and the connections I made, they're all actually implemented on the device. So if you had a ASIC device and if you change the regular expression, I could not have done that.
Okay.
Okay, so I think that for the third problem, I am exploiting the FPGA programmability through static programmability as an expression is given to me. For the other two, you could have done the same thing on ASICs too.
Thank you very much.
Any other questions for Professor Prasanna? Anybody want to send me a question maybe via chat or Okay, I guess I have one question, Professor Prasanna, and that had to do with this notion of pipelines. I think from a conventional microprocessor perspective, I kind of understand what pipeline stages are. In the context of FPGAs, and you talked about the pipeline stages. Are they simply the sequence in which the FPGA sort of the gates are arranged, or I mean, what are the pipeline stages, and how are they defined here?
Right. So I think whatever I talked about in the examples, look at a pipeline stage as doing some kind of a comparison, deciding which particular path to take in your tree structure, the search tree that we have. Therefore, each pipeline stage is a very simple, gets the input, maybe a 16-bit number or a 32-bit number, and compares against a key stored at that stage by accessing the local memory, and then forwards to left or right by computing the next address to be used in the next stage. That's a simple pipeline stage. That particular stage, conceptually what we have is going to be mapped into the logic resources we have, and the connections between the pipeline stages is going to be performed by using the routing resources we have on the FPGA device. So whatever conceptually we talk about is going to be actually realized by using lookup tables and the routing resources and either the distributed RAM or the block RAM for implementing the memory in those systems.
I see. Okay. Okay. Thank you. I have one more question, and that has to do with I guess in terms of trying to understand the process for how you come up with these kinds of designs. If I were to sort of think about it, you focus on a problem, let's say IP lookup or packet classification or DPI, and you try to map that problem into sort of your domain. You come up with an architecture such as the ones you showed, and then in terms of, and then you of course come up with an implementation for which you showed the results. How much of this process can be automated once an initial algorithm is defined?
Mm-hmm. So I think it's a good question. There are some steps can be automated. For example, we are doing some work in which, if we fix our pipeline architecture as my target, how do we optimize the pipeline stages? What kind of searches to be performed given a choice of searches? So we can pose some of these things as some kind of a mathematical programming problem and solve them. So that's there's definitely some automation can be performed, but if you fix it. But the intuition that we bring to the table in terms of what data structures to be used, what kind of a target architecture should be chosen, all of that is very, very specific to your particular problem, the particular line of thinking we have, whether we should use tries or trees. All that is a manual process of discovery.
I see. So if Xilinx or Altera were to come up with sort of a, the next generation FPGA, would there be substantial rework in the algorithm, or would it simply flow through? Conceptually, the algorithm does not depend that much on the technology. We said we have a pipeline architecture. We said that controlling the memory power is important. Why? Because most of the power is dissipated in the memory. Unless in the newer technologies, the memory power consumption dramatically is so less that some other factors come into picture, these ideas will not work at that time. So I think at this time, the memory is where most of the power is dissipated, and that's where we're attacking the problem. Thank you. Folks, any further questions for Professor Prasanna? If not, we've taken up extra. Go ahead. Any question?
I can do one more if I could. In the early part of your presentation, you talked about, let me say, what should I say, cascaded FPGA logic. And when, for example, implementing the add or other circuits, you asserted that they were constant time algorithms, but it seemed that, for example, the number of gate closures that you had to traverse were linear in the number of bit positions, and so it seemed that there was a certain non-constancy in the solution time for some of those algorithms. So I was trying to get a little better handle on the assumption that leads you to those constant time results.
Right. That's a very good question. This question is applicable not only to the reconfigurable mesh, it is also applicable if you were to, for example, build a butterfly network or a hypercube network. So in all of these cases, we are going to have either long wires, or in the case of reconfigurable mesh, possibly long connection of switches coming in the way, on and off switches. So I think the basic assumption of the reconfigurable mesh model, as is the assumption in the other models such as the hypercube models and the multidimensional mesh connected computer models, we are assuming that every communication that happens through a link may consist of on and off switches, is going to be unit time. And under the unit time assumption, you get those performance results. But that is not the only model. For example, you may feel like if a signal goes through k number of gates, the delay should be some way related to k. For example, there are what are called logarithmic delay models. You say the basic assumption there being that if you go through k switches, your delay is proportional to log k. So you can scale these results accordingly from that perspective. There are results of that nature also in the literature that is talking about variations of this basic model, where the delays are explicitly modeled and you get different performance numbers, and then obviously you cannot get constant time delay results as I showed here if you assume longer delays for those paths.
Thank you.
Any further questions? If not, thank you very much, Professor Prasanna. I think we began a tradition a while ago to sort of do a virtual clap. So for all of you who have unmuted your phones, let's do a virtual clap for Professor Prasanna.
very much. Appreciate the opportunity, and I'll be happy to remotely or offline answer any questions people might have.
Yeah, so just if you can send me your slides, what I will do is I will upload the slides to the website. I will also save the recording away. I know there are at least 2 people that for some reasons related to their company firewalls could not actually access the presentation, but we're just able to hear the audio. So you should be able to access that on YouTube. So with that, thank you so much, everybody, and in particular, Professor Prasanna. Have a great day.
Thanks, everyone. Bye-bye now.